All right, this is lesson 5.3. Our formulas we have are all on your formula sheet for mean, variance, standard deviation. You'll notice that the formula for the mean of a distribution is the exact same formula for what we call the expected value. So I'm going to give you an example of both of those. So mean and expected value are really the same thing. Number one, on lesson 5.3, which is page 253. From past experience, a company has found that in cartons of transistors, 92% contain no defective transistors, 3% contain one defective transistor, 3% contain two defective transistors, and 2% contain three defective transistors. So a place that builds radios, for example, like maybe Rockwell or someplace like that, they get these transistors in maybe, and they're going to use them, and they want to use them, and they want to know how many should they expect to be defective or bad. And maybe, if they get too many, they go to a different supplier. They order from somebody different. So I've got a table set up here where X is going to be the number of defective transistors. They said the probability of 0 would be 0.92, the probability of 1 defective is 0.03, the probability of 2 defective would be 0.03, and the probability of 3 defective transistors is 0.02. So you put your outcomes in the top column, and you put your probabilities, P of X, in the bottom column. That's called a probability distribution. All right, we learned to write those and create those yesterday. The question in this one is, find the mean, variance, and standard deviation for the defective transistors. So for the mean, we're going to use, this is our population mean. We're going to use this formula, the sum of X times P of X. So that means what we're going to do is multiply our X's times our P of X's. So we're going to do 0 times 0.92 plus 1 times 0.03 plus 2 times 0.03 plus 3 times 0.02. So notice that we're multiplying our x's and our p of x's first, then this symbol, the capital sigma, tells us to add all those together. So you can just type that into your calculator, and of course 0 times 0.92 would be 0, 1 times 0.03 would be 0.03, 2 times 0.03 would be 0.06, 3 times 0.02 would be 0.06. Add those together, you get 0.15. And if our outcomes are in whole numbers, then we should round our measures, our parameters actually, one more decimal place. So I should round that to what? This is in whole. These are in whole numbers. I'm going to round these to the nearest tenth, so that would be rounded to 0.2. What that's saying is, on average, they should expect 0.2 defective transistors for every carton that they buy. So less than 1, 0.2. That's the average number of defective transistors they'll get per carton. The variance. The variance is going to tell you how much that's going to vary. Are they consistently going to get 0.2 defective transistors, or is it going to vary a lot? Okay. Of course, you couldn't get 0.2. You can only get whole numbers actually. But so our variance formula. Here's our symbol for variance. Is the sum of x squared times p of x minus the mean squared. So for that, we have to square our x's. So we have to take 0 squared times 0.92. Could you guys type this in your calculator as we go here? 0 squared times 0.92, of course that would just be 0. Plus 1 squared times 0.03. Which I guess would just be 0.03. We maybe don't need our calculator yet. Plus 2 squared times 0.03. Plus 3 squared times 0.02. Separate it off. There we go. So actually, I think we could probably do this. So 0 squared is 0 times 0.92 would be 0. 1 squared is 1 times 0.03, that'd be 0.03. 2 squared is 4 times 0.03 should be 0.12. 3 squared is 9 times 0.02 would be 0.18. Add those together, you get 0.15 plus 0.18 be 0.33. Does that sound right? Okay, 0.33. Now, what did I forget? I did this on purpose because this is a really common mistake, and I want to make sure you notice it, make sure you don't make this. What did I not do in the formula here? I didn't subtract my mean squared. That's probably the most common mistake. Don't forget to subtract your mean squared at the end of this formula. Don't forget that. Okay? So I need to subtract. Now, use the 0.15. Don't use your rounded value, use your exact value, otherwise it might throw off this answer. So I'm going to use 0.15 squared. I'm going to subtract that off of this total. What's that come up to? Tell me what that comes out to. Take 0.33 minus 0.15 squared. 0.3, is it? 0.3075, and then we're going to round it to the nearest tenth because our outcomes are whole numbers. You always go out one more decimal place, so 0.3 transistors. Well, we won't worry about labeling. This label here is transistors. This would actually be transistors squared because we squared the number of transistors. But all right, and then finally, our standard deviation. What do we do to the variance? And let's use this number here. What do we do to that number to get our square root? Let's take the square root of 0.3075. Notice I don't want to use the rounded number. That'll throw off my answer. So use this whole decimal. And what's that come out to? 0.55. Like that. So that'd be about 0.6 transistors. Let's see if we forgot anything. Okay, about how many extra transistors per day would the company need to replace the defective ones if it used 10 cartons a day? So this question is saying, if they use 10 cartons a day, and they're going to get an average of about, and I'm not sure if they use 0.15 or 0.2, I'd probably use the 0.15, but if they get an average of 0.15 bad transistors out of every carton, and they use 10 cartons a day, how can I figure out how many transistors they're going to get that are defective every day? Yeah, take 0.15 times 10. So that's going to be 1.5, which should round to 2. So about 2 transistors. So they will get about, on average, 2 defective transistors per day. And that's just by taking the average amount per carton times the number of cartons.
How do you get the 0.2 or 0.6?